Hi, my name is Opeoluwa Wonuola Olawale. I am a PhD student of the Advanced Energy Systems program at Mines. I will be talking to you today about who is most likely to interact with demand flexibility at home using socio-demographic predictors from the American Time Use Survey. First, I will explain what the problem is and the state of the art in the literature. Then I will share our methodology with you and provide conclusions from the results we got. So, what is demand flexibility? This is the ability of buildings to reduce peak demand or modify load shapes A, B, and C in response to utilities request or price signals as illustrated at the top left and middle. DF also allows more renewables in the grid. In fact, up to $14 billion in annual grid costs could be avoided if only DR reached its potential. However, I want you to look at the 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 uh, the bottom left figure. Despite the billions of dollars spent on customer incentives over the years for demand response, less than 40% of the estimated DF potential was realized. Two big issues: poor participation and high override rates. To help you understand, imagine you finally enrolled in thermostat demand response, and while you were sleeping or resting, you got a text from the utility about pausing your heater just because it's critical peak period. How likely do you think you would respond or override the request? How do we tackle this problem? What if we understand DF customers or who is doing what the most and when? What do people prioritize when it comes to demand flexibility? Should there be a roster? Could we get better participation? So notice that we focus on residential buildings in this study. This is a sector that consumes over 20% of the electricity generated with over 135 million customers. So going back to what I said, DF programs suffer low participation and overrides as you see the difference between the top figure estimate and the actual DF estimates at the bottom. So when it comes to understanding what people do during critical peak period, we know very little. In fact, social scientists argue rightly that it is not our love for energy that makes us use electricity, but the activities that we do daily. Oh, this is known as the social practice theory. You could just think of it as energy use resulting from activity, our behavior, and equipment. Of course, there are several models. Most of them are stochastic and they are very expensive in terms of computational resource and more like black boxes. Of course, there are also other approaches that assume average time that is spent on activities. In general, demographic details are either ignored or lumped without knowing which matters more. So to put it simply, the literature and the utility industry still lack broad insights into the human components affecting DF adoption or human interactions with DF. So, based on the gaps in the literature, our focus is to find what demographic variables might tell us who DF should focus on and when. First, we collected the one-day data on occupant activity and timing, more like their behavior, for about 200,000 respondents in the 2003 to 2018 American Time Use Survey, ATUS. We use ATUS to represent the US and even kept aside test area. After this data preprocessing, our next major step was to identify and select DF-related activities from over 420 recorded activities in ATOS. For instance, look at DF thermostats to be relevant to when you're just home or sleeping. The next thing we did was to explore several demographic variables that are usually discussed in the literature, and we focused on 17. These 17 variables are simply easier to find in the public domain. We also controlled for fixed year, season, weather, and location effects. Then we evaluated the machine learning regression models on choice and duration of these activities. And finally, we check for statistical significance of the selected demographic variables using post-selection inference tools. So to test our predictive models, we used separate test data that the models had not seen before. more like a service area that utilities or DF programs might be interested in. Of course, our test area has 4,225 people in total. That's in orange. And for this presentation, we are looking at the different periods on a weekday. The probabilities of activities on the x-axis for each activity on the y-axis across the different periods in each plot. For instance, it is more likely to be just home needing your thermostat on during critical peak period with 0.24 probability and more likely sleeping during the early hours of the morning during off-peak period with 0.36 probability. It also makes sense that it is more likely to be doing cleaning, including taking showers in the mornings during off-peak. We notice that only a few report pool use and is the least probable activity. The choice model predictions in blue, they do quite well in predicting the mean probability of each activity. Can look at this small inset plot with showing less than 20% error margin. We, however, noticed for computer use and laundry during off-peak period on the far right that we are off by at least 20%. So we're thinking that the tiny probabilities of doing this activity during off-peak period could be the reason for this, or could mean that both computer use and laundry choice are indifferent of who you are. And so when we look at the time people spend on activity, we notice that the amount of time changes from critical peak to off-peak period. It's more like looking at the day of a typical American. As expected, people sleep longer at night once it's past 7 p.m. during peak night. The different activities in total summarize how people use their time during different periods. The first takeaway is to notice how more time is spent on all activities except sleeping during critical peak period compared to off-peak period during the during peak period on the far right. We can tell that people generally their um, prioritize activities in the evenings between 2 p.m. and 7 p.m. Ironically, this is when utilities find DF resource critical. So this emphasizes the need for us to know who to focus on. The other key takeaway from these duration models is how closely we are able to predict how much time people spend on activities, including sleeping, just on cleaning, cooking, being home, or being away, and exercise throughout the day just by knowing their demographic characteristics. You notice these inset plots showing good prediction within the plus or minus 20%. It now also means that we can monitor time use differences if people change or if a place changes. We can also apply this framework to weekday versus weekend, for example. So these are excerpts from our several model runs to find which social demographic variables are significant with choice and duration of DF activities. We looked at the top 5 socially significant predictors across different time periods for different activities and ranked them by their marginal effect and their beta coefficients. So we found these 13 social demographic predictors consistently across all of the models. We can summarize this as your personality, your family dynamics, your social status, education, and race. So the sorting of these marginal effects for 3 activities during critical peak period looks something like this. To demonstrate applicability to DF, let's look at 2 common DF programs such as connected thermostats and smart water heaters. What do these regression coefficients tell us? For instance, gender. This means that you're most likely to get more success with connected thermostats with women, but smart thermostats, but smart water heater with men during critical peak period, given that women spend about 24 minutes less than men sleeping and 7 minutes more engaging in cleaning activities during peak period. And when you look at labor force status, it's more likely for someone who is employed to respond to your DR thermostat event call during critical peak relative to someone who is not in the thermostat who is not in the labor force, who generally spend about 23 minutes more at home during critical peak. The one that is quite fascinating is how a postgraduate sleeps 65 minutes less than someone than someone to compared to someone who has less than high school education. So it means that we can likely switch things off remotely while the other person is sleeping. While the mechanisms for this needs to be tested, these results offer deeper insights into timing and priorities for different people, unlike before. There's simply so much we can learn from these different subgroups during different periods. So, in conclusion, so far, we showed you how we leveraged and connected existing data to knowledge gaps in creating a framework to answer the questions that we asked initially. We also demonstrated how residents' behavioral pattern changes with activity and by implication changes with DF technology. We also showed you good prediction accuracy simply by using publicly available demographic data up to national scale. We also found out that gender, hermit lifestyle, social status, family dynamics, education, and race are key demographic predictors after sifting through more than 17 demographic factors. It tells us that we have a chance to improving our estimations of demand flexibility by using publicly available data. So yes, we're still far from integrating these insights into DF estimations. We are closer to better understanding how people's behavior could impact how we frame our energy solutions to customers. We're hoping that our work informs future messaging schedules that help demand response reaches its potential. Here are my references. Thank you so much for listening. I'm so happy to hear questions. I'll be so happy to hear questions and thoughts you have via email. Thanks.